Okay, now let's begin my presentation about my project. My project title is Wireless Big Data Transceiver for IEEE 8.11 networks. My name is Wang Linghui. And first, let me introduce my motivation part. As we can see from this paragraph, this diagram, this graph, with the big data rate is increasing, we could see that the MAC layer efficiency is decreasing accordingly. This is because the large overheads are added to each frame transmissions. So, if the data rate is increasing, the short data packets may become less efficient. And in this case, it cannot satisfy the requirement of the delivery of large volume of data. For example, the big data applications involving data exchange between multiple data sources. So, this poses a new challenge for us to enlarge the data payload size. How to enlarge the data payload size in this case? Firstly, in our work, we plan to implement a single-in and single-out OFDM systems on NI-level platform. Based on these systems, we can modify the system's mechanisms related to the information transmission and recovery part to enlarge the data packet size to improve the throughput performance of the system. So in this system, we use NIUSRP, which is a transceiver which can monitor actual single-point communication waveforms. It can send waveforms with a large frequency range. And in this case, if we change the parameter in LabVIEW, it can automatically download its change into the USRP. And in this case, we can combine these things as a whole system for us to use. So, what is the SISO OFDM systems? The SISO means single in and single out, which means that only one data stream and a single data channel here. As for the OFDM systems, it means orthogonal frequency division modulation. The basic principle of OFDM is to split a high-rate data stream into a number of low-rate streams that are transmitted simultaneously over a number of subcarriers. The advantage is that it can eliminate the problems of inter-symbol interference, low spectrum efficiency, and frequency selective fading. The difference from the normal system, we can see that in this system, the channel is divided into n subcarriers to avoid intercarrier interference. And since each of the subcarrier is orthogonal to each other, hence the bandwidth efficiency is very high in this case. Apart from that, to diminish the effect of inter-symbol and intercarrier interference, we can accomplish this thing by copying the tail of the signal and glue it to the front. And in this case, we can diminish the effect of inter-symbol and intercarrier interference. Okay. As our project aimed to enlarge the payload size. Hence, we mainly focus on the information transmission and recovery part, which related to the following algorithm. First, I will introduce the short training sequences. We can see from this structure that there are two training sequences appended before the following OFDM symbols. And these preambles are used to estimate the following symbols. We use the following two algorithms to utilize the training sequence to estimate the following symbols. The first one is Schmidt and Coase algorithms, which use periodicity created in sorting sequence to perform the frequency of saturation and frame synchronization. And second one is channel estimation. It uses the information from the training sequence to estimate the channel conditions. There are several methods of the OFDM channel estimation. First one is the MMSE and also the modified MMSE. In this, our system we just can limit the minimum mean square error. As for the measurement tools, as we said before, we utilize the NI lab view to develop a program of OFDM, which is a visual programming language from National Instruments. Hence, how about the results of the first semester? Actually, we already have constructed the whole SIL OFDM in live view systems, which already can transmit more data packets with good performance. And these two graphs basically introduce the some part of our OFDM transmitter and the receiver. These are the sample of the lab view. We can have a look at that. As for the future work, actually, as we mentioned before, the end goal is to implement a modified system which can send large data packets. So we need to modify the method of inserting the short sequences or pilot into the OFDM symbols, and also change the respective methods of channel estimating and synchronization to deal with large data packets. For instance, we can insert a new short training sequences behind the large packet size or in between the large packet. In this case, we may perform a better channel estimation or synchronization if we use more shorting sequence. But accordingly, we need to modify these algorithms also. So this is our overall project. And the first semester's result that we have constructed those single using algorithm, and the next semester we mainly focus on how to modify the transmission recovery part in order to get the large packet size to be sent with a high throughput. Okay, thank you.